So in this lecture, I'm going to talk a little bit about how to synthesize a function generator analytically through 3 precision positions. So starting off, I have a generic 4-bar, and like we had talked about before, we can represent the different components of it as vectors. So I've got the W and the Z on the left side of my mechanism, and the W star and the Z star on the right side. Now, in a function generator, recall that all that we're interested in is coordinating the rotation of my input with the rotation of the output. So the input link and the output link. In other words, the rotation beta, which is the rotation of the W vector, and the rotation gamma, which is the rotation of the W star vector. That's all I'm concerned about. I don't care about what the shape of my coupler is. So because I don't care about the shape of my coupler, what I'm going to do is I'm going to collapse it by saying my Z star vector, that right side of the coupler, so the Z star vector is going to be set to 0. And as it does so, then Z vector will end up at the tip of the W star vector. So something like this. I'm going to collapse my coupler down and now just have a 4-bar without any shape to my coupler. I've removed the Z star vector, setting it equal to 0, simplifying this slightly. Now let me look at this in the first position and the j'th position. So here it is in the j'th position, and now I can start to set up vector loop equations around this, similar to what we did when we had path and motion generation. So first of all, I'm going to measure also the angle of the rotation of the coupler. I need that to develop my system of equations. And I can say that I use my rotation operators to describe these vectors in the displaced position, or the red position as it's written. So I've got the displacement of the W, of the Z, as well as the rotation of W star, which is e to the I gamma j. So let me use this now to develop a vector loop triad, we call it, because now I have 3 different vector loops that I'm going to be adding up. Similar to what we did before, I'm going to go ahead and move up the displaced position. So I'll start here at the origin of the left side. I'll move up W e to the I beta j. I'll add Z e to the I alpha j. I'll subtract off W star e to the I gamma j. I'll add W star. I'll subtract Z. I'll subtract W, and that's all equal to 0. So all I'm doing is I'm simply adding around that loop, forcing it all equal to 0 because I'm coming back to that same origin. Let me do a little bit of shuffling of these and combine them into terms that we're used to seeing in that standard form equation where I get these rotation operators minus 1. So I've got that for W, Z, and W star. And then once I have it in this form, I can start to say, how am I going to solve this thing? Well, it depends on how many precision positions I'm going to have. So in the case where I have just 2 precision positions, I have this one triad equation, which is a vector equation. So it has 2 scalar components to it. And my unknowns are the W vector, the Z vector, the W star vector, as well as the rotation of the coupler, that alpha 2 angle. So I've got a total of 7 unknowns. So 7 unknowns, 2 equations. I have to make a total of 5 free choices, a huge number of free choices. Very rarely will you see a function generator being synthesized through 2 precision positions. It's just not all that useful. How about when I go to 3 precision positions? I add one more triad vector loop equation, which gives me the equivalent of 2 extra scalar equations. So I have 4 scalars. I have all those same unknowns, plus I add alpha 3, which gives me then a total of 8 unknowns. So I then end up with 4 free choices. And as I jump to 4 positions, I add one more vector loop equation, equivalent of 2 scalar equations. That takes me to 6. I add alpha 4. That takes me to 9. So I end up with 3 free choices. And I think you can see where this pattern is going. Now I'm going to 8 scalar equations, 10 unknowns, and 2 free choices. Finally, as I go to 6 positions, I go to 10 equations. I get 11 unknowns and 1 free choice. And believe it or not, we can actually synthesize a function generator through 7 precision positions by getting up to 12 scalar equations, 12 unknowns, and then having 0 free choices and a finite number of solutions. Quite challenging actually to solve the system of equations, but it is possible to do so. Now, with all that said, you might say, which equations do I really want to have to solve for? Well, it turns out that any number of precision positions fewer than 4 will give us a linear system of equations, making it quite easy to solve. And anything higher than 5 or more will be a nonlinear system of equations. And we'll talk about how to solve both of them in this class, but we're going to start off with the simpler case of the linear system of solutions. So since we've been talking about 3 precision positions for both motion and path with prescribed timing, let's do the same thing here for a function generator. And I'll say, what about 3 precision positions? Now, to help me out, make some of these free choices, I'm going to go ahead and pick the magnitude and the angle of the W star vector. And I think you'll see why I do this in just a moment. So by picking the magnitude and the angle of the W star vector, I can move this term over to the other side of my equation. And now you'll notice that by having this term on the other side of the equation, I can equate that to a displacement vector, delta J. Now this displacement vector, delta J, is basically going from this point right here up to this point right here, and that is my delta J vector. That is the same as W star times its rotation operator minus 1. Now, why do I want to do that? Well, you'll notice that that part now that I just boxed, that is the standard form equation that we've solved both for motion generation and path with prescribed timing. So if we can get it in that standard form, we can use the same code that we've generated for these other tasks for function generation as well. It makes my life quite a bit easier. And then I can just say, if I'm in 3 precision positions, let me go ahead and pick the alpha angles, because those would be my unknowns, and then I can solve for W and Z. So ends up being the same way that we solved both the motion problem as well as the path with prescribed timing problem. Quite easy to do. So hopefully you've got the tools to mathematically take care of that. Now, one of the questions becomes, what is the impact of picking the magnitude and the angle of the W star vector? If I went ahead and did that, what are the impacts of that free choice? Well, think about it this way. If I was to go ahead and synthesize a function generator, and again, remember, a function generator is only concerned about what the rotation of the input is relative to the rotation of the output. I really don't care what the orientation of my mechanism is. And by picking the W star vector, that is setting up what is the magnitude or the scale of my mechanism and what is the initial rotation angle of my mechanism. So I could take any of my function generators, I can rotate them, I can scale them, make them bigger or smaller, and basically get the ground pivots to land where I want them to, and then that forms the function generator I want. So the W star vector, by picking that, I really just set up the magnitude and scale of my function generator, and once I synthesize the function generator, after the fact, I can rotate and scale the entire thing, the W vector, the Z vector, and the W star vector. I can rotate and scale all 3 of those vectors such that I can get it to fit in at the ground pivots I want it to, or within the space that I'm interested in. So that is one special feature of function generators, is that they are rotatable and scalable, whereas the other 2 tasks are not.